For inviting me, and thanks everyone for coming. So I'm going to use cost and reward interchangeably because I like to not differentiate too much between controls and especially optimal control and AI. But yeah, I figured, I know this is a seminar where we usually talk about the intersection between learning and controls, and that often means things like how given a cost function that you set for a system, how do you go about enabling the system, despite the fact that it doesn't understand how the world works and so on, to be able to actually perform well under that cost function or under that specification? I wanted to talk today about something a little bit different, which is essentially this cost function itself, and the learning that arguably needs to go into figuring out what the right cost function is for a particular any particular real world task that you want the system to accomplish. And so it's a slightly different take on learning for control. And I wanted to kind of give an idea of how I got started thinking more deeply about this problem. So I was working on autonomous cars, and we set up a little simulator, and we had this kind of autonomous car here in Orange. And we had a human-driven vehicle in white. And we said, okay, I know what to do. I'm going to write down a cost function. We're going to run model predictive control, and we'll get this car to do its thing. And so the first attempt at a cost function was, stay on the road and all the safety stuff, don't hit things, and be efficient. Make progress in this car. In this case, the car had to turn left. Eventually, it had to get itself into the left lane. So it wanted to make progress along that. So those were roughly the terms in the cost function. Emphasis on efficiency subject to these safety constraints. What does the car do? Well, it predicts that this person in the white car is going to keep going in their lane. Its safety says, I can't crash with them, so I have to stay out of the way. And so the optimal thing to do ends up being to brake, slow down, and then merge behind the human. This is not super great for autonomous cars if they always do this, because they often find themselves in situations where there's not just one person in the left lane, there are many people coming into the left lane, and yet you still have to get yourself into the left lane in order to take that turn. And so if you wait for everyone until there's a big enough gap in traffic, then you end up with either waiting and then pissing off people in behind you who are trying to keep going, or you end up kind of keeping on going then missing your exit. And if you look on the internet, people make fun of autonomous cars for doing this silly thing from time to time. And this is in contrast to what humans do. What humans do is we kind of invent this third option, which is to kind of nudge ourselves in there, even though there's not a big enough gap in traffic. It's like, okay, we're just going to nudge ourselves in there. Why? Because we know that the person behind will be able to slow down slightly and accommodate us. And so we worked hard to give cars the same kind of ability, this notion that what a car does actually ends up influencing what a human does. It's not like you can just predict what people do and stay out of their way. The moment you start acting, that can affect what people end up doing. And so we sort of thought about it as an under-actuated dynamical system, a very simple one in some ways, because you kind of have direct actuation on the robot, and then you're influencing what happens with the human degrees of freedom, but you don't have actuators on the human. You don't control what the human does. And so we, had a model for how this influence happens, what the dynamics of the system look like. We did MPC. And now, lo and behold, the car doesn't have this problem anymore. But there's a flip side, which is if the car can gain a little bit in efficiency, what it will do is it will cut you off and force you to decelerate at 7 meters per second squared, because that's more efficient for it. As long as it's not a safety problem, it has no problem doing that. And so that's an issue for the person who's being cut off. We want cars to do this when you can sort of decelerate a little bit and it's not a big problem for you and it's a big gain for the car. But if it's a little gain for the car and a lot of struggle for you, a lot of inconvenience for you, that's not acceptable. We don't want our cars to be jerks, basically. And so what do? Well, we had to revise the cost function. We said, okay, the cost function is not communicating, incentivizing our car to actually be courteous to other people. It turns out this is another thing that we care about, courtesy. So we added a term in the objective for courtesy. And then, the car no longer cuts you off all the time. It sort of balances that with its own efficiency and so on. And that's great. But then we put the car in a four-way stop and at an intersection. And it doesn't just go. It doesn't wait for you to go. What it does is it starts inching backward from the intersection in order to be courteous, in order to make it more efficient for you to go through. And so I kid you not, people go through faster through the intersection because, they can do it safely. The car is no longer a threat of being in their way, and that's great. But the problem is, if you have someone behind you, or if you have a passenger in your car, that person is now freaking out, wondering why the heck is their car going backwards from the intersection. So there's still something wrong with the cost. We're still not capturing everything that we cared about, right? We're not capturing things like passenger comfort or legibility to other drivers and so on. And so this is one domain out of many in which I'd say we're getting good at taking a task specification. I use rewards or costs, but people use goals, people use constraints, loss functions, etc. Whatever your sort of methods of choice are, taking that specification and turning it into behavior via optimization, via constraint satisfaction, via REL, via whatever your method of choice is, right? So that's something that we're making progress on. It's not perfect, but we're getting there. But what's really, I think, somewhat ignored is what we sweep under the rug is just how hard it is to write down the correct task specification to begin with, right? How do you capture comfort for an autonomous car? How do you trade off between safety and efficiency and not crossing the double yellow line, right? We sometimes think that constraints will save us, but they're just as bad, right? What threshold do you set on the probability of a collision? And what happens if you can't both meet that safety threshold and cross and not cross the double yellow line, right? You have to make some sort of trade-off there. I gave you the example from some of my own work, but you kind of see this everywhere. On the AI side, you see this, for instance, this glorious video from OpenAI where they trained an agent, a boat here, to play in this boat racing game. And I think it was some policy gradient method. But what the boat does is not race very well. What it does is it finds this policy where it sort of gets stuck in this loop. And you might think, PPO guy, has done something wrong. There's a bug with DeepRL. Turns out, no, there is no bug. It works as intended, quote unquote, if what you intend is for the boat to get a lot of points. Because getting a lot of points was the reward function that this boat is optimizing. And it turns out that by looping around and hitting these green thingies at the right timing, these green thingies give it like 1,000 points every time. And so it's just accumulating points. And so it's doing exactly what we asked it to do. Now, unfortunately, that's not actually what we intended. We intended for it to race and then actually win in the game, right? I'll say this is not a problem as you're still designing the system. You'll catch this, you'll revise the reward function. But it is a problem if you don't catch some things and then you deploy a robot or a system this way. And that's the thing that I'm concerned about. So I think the problem stems from the fact that I think we'd lie a little bit to ourselves in AI and in optimal control. We pretend that the problem is you have an agent, there's a state space, the agent takes actions, the actions affect the state, there's some reward function that falls from the sky. And the problem definition is basically finding a policy that optimizes that reward function cumulatively in expectation. And so we do this because, it's a way to make progress on concrete problems, but unfortunately, that's not what the real problem is. The real problem is, there's a state space, there's an action space and so on. And there is a human who wants something. And the agent's job is to do what that human wants. So the reward function doesn't fall from the sky. It's internally implicitly in someone's head, and they'll try to explicate it, but they'll probably not do a perfect job. So I think, it's not AI and optimal control shouldn't be about optimized specified reward or cost. It should be trying to optimize for this, implicit intended thing that the person wants the system to be doing. And so we should try to build systems that do that. What does it mean to build systems that optimize intended reward? Well, if I try to make it a little bit more concrete, what I'll say is we'll have to parameterize this reward function somehow. In this talk, we'll use theta. This is my notation of choice to refer to the parameters of the reward function. So you can say the reward is a linear combination of features that I know, or the reward is a deep neural network with state and action as input. We're gonna call theta the weight in that model, right? So those are the parameters. And what's hard is that the robot doesn't get to observe theta directly. This is not directly observable to the robot. And so instead, if we're to do this right, we're gonna acknowledge that we have uncertainty over what theta is and maintain some sort of distribution that we try to estimate somehow. If you think about what we do now from this lens, it goes something like this. If the human, the designer, tries their best to form a theta, right? We either specify it by hand, or we sort of train some features and then combine them by hand, or whatever it is, we tune that up, we do our best, and we call that, and that's the reward function. Now, that ends up being not exactly the same as theta because of human error, but nonetheless, our robot pretends like it is. Our robot pretends like it somehow has this perfect sensor, and theta becomes the definition of the theta tilde becomes the definition of the reward function, essentially having this belief that's like, okay, if you tell me theta tilde is the reward, I'm going to believe you. So with probability 1, theta tilde is the correct theta, and then I'm going to go and optimize that. And if I didn't get it right, then my robot is going to be deployed and optimize theta tilde instead of the actual theta that I want, sort of, in perpetuity. And on top of that, right, even if I try to help it along afterwards, it's not going to listen to me. So here's the situation where imagine that. So I have this robot arm. Its cost function is be efficient, but also maximize distances from objects around in order to avoid collisions like the table and so on. And so I see this robot and I say, well, you're carrying this mug, but you're keeping it very high up. And I get worried because if you drop it, maybe it's going to break. So I want the robot to keep the cup kind of closer to the ground. What I might do is I see it move and I might intervene. I might actually push on the robot and bring it closer to the ground, to the table. And if I run an impedance controller, then the robot actually complies to that and everything's great. The problem is that this is very temporary. The moment I let go, what does the robot do? Well, it runs optimal control to optimize the cost function that its engineer specified. And that says maximize distances from the table. And so the robot's like, okay, I'm so glad you let go now. And I get to go back to doing the task in the actual optimal way and, not have to deal with you, disturbance creator. So I keep pushing and it keeps popping up and I keep pushing and it keeps popping up, right? I call this sort of stubbornness if I were to anthropomorphize it. So I think the bottom line for me is that we read too much, we overlearn from the reward that's specified to the system, which is not perfect, but we somehow trust it as if it's magically perfect, because people are perfect oracles. And then there's other information that we just leave on the table. Like, my push for the robot, it's like, whoa, that's a disturbance. I will reject it and go back to the optimal thing to do. So we underlearn from other sources. And so what I've been fascinated with lately has been, how do I fix this? How do I kind of learn the appropriate amount from all the sources that are there? Okay, so people might physically interact with the robot. They might say stuff in natural language. Imagine that the robot's about to go through a puddle of water, and I know that if it does that, it will break, so I switch it off in a panic to protect it. I'd argue that even that is very useful information about the reward or the cost function, right? Even if all I was thinking about was stopping the robot in the moment so that it doesn't fall in the water, I'm giving the robot this really valuable piece of information. When I turn it off, it should figure out from this that generally it's probably a bad idea to go in the water, right? Since I preferred for it to be turned off than to do that. Even though the person didn't tell the robot all this, right? Them stopping the robot was, I think, a pretty good signal along this direction. My favorite example of a source of information that we're leaving on the table is the environment itself. So imagine that someone asks you to clean up a room. And as you enter the room, you see this beautifully laid out house of cards that someone built there. Okay, you didn't see the person building it, but you see the house of cards. I will bet you that even though the person didn't specify, oh, clean up the room, but don't clean up my house of cards, each and every one of you would kind of read between the lines and leave the house of cards there. And so somehow there's the very existence of the house of cards is already evidence that the human cares about it and doesn't want to destroy. What's up with that, right? So the environment is speaking to the robot about what the cost function should be. So I think through what we do, through what we say, even through how we set up our environment, we end up leaking information about what we want and therefore about what the robot should optimize for. And then I think this information can fill in the blanks of what we forgot to specify ahead of time. And the question is, how do we enable the robots to capitalize on this, to extract this information that people are leaking left and right? How do we get them to sort of stop over relying on the specified rewards and relying more on these sources? In other words, how do we go from observing the feedback from the human to doing a belief update for this parameters theta that is our estimate of what the reward should be? And what's hard about this is that we need to kind of give the robot what we might call this observation model, this human model that links the feedback with the theta, right? What's the probability of this feedback condition on any particular theta? Then I can just run my Bayesian update and infer something about theta. So given the reward function, what feedback do we expect? And we need a model that works for all this diversity of feedback types. And so kind of now that we're on the same page about what the problem setup is, like we have uncertainty about the reward parameters theta, we use human feedback of various forms to learn about theta. What I want to do for the rest of our time together is to kind of dive into one of these feedback types first, talk about how we might do this in the special case of a specified reward. If the person specifies a reward, how do you think of that as mere feedback as opposed to definition of the reward function? And then towards the end, sort of pop back up and show you how you might be able to generalize this to these other types. Okay, so when you specify a reward for your robot, what does it mean for the robot to sort of ignore that and say, no, this is not the reward, this is just evidence, right? What am I talking about here? Basically, the question is, how do you mathematically capture this process that makes the designer not end up with the right theta as they're trying to specify the theta? It's in their head, so why are they specifying theta tilde? Why are they giving us theta, right? What goes wrong there? And I thought about this for a while, and it's not that, you take your true theta and add some Gaussian noise and that becomes theta tilde. It's not as simple as that, right? There's some actual systematic errors that might happen as you're trying to design a reward function. And I think a lot of what drives the suboptimality or the difference between theta and theta tilde is that as a designer, you only get to look at some development set or training set of environments, and you decide your theta tilde based on that limited set. You don't look at every possible thing that might ever happen. We can't do that. We're limited, right? We can't imagine for any environment that the robot might face. We don't anticipate that there'll be like turbo boosters popping up at regular intervals, and therefore that might lead to a loop. So I have to tell the robot that it's not just points, right? Like it's hard to think about all the situations. And so going back to this boat example, with the boat taking a loop for points, right? So what goes on when you get surprised by this behavior at sort of at test time, at deployment time, is this difference between development and deployment. we're not going to worry about bad behavior during development because the designer is going to fix that, but we are going to worry about bad behavior during deployment. So imagine that the boat did this thing, loopity thing at deployment time. It's because it encountered this environment where it had these options. It had the option of racing and winning and getting some number of points, say 20,000, but there was this other option, this other behavior, this other policy that was to do this loopity thing, not win, but gain even more points, say 50,000. And it chooses to gain more points because why? Because we told it optimize score in the game. And so the question is, how did we mess up and say optimize score in the game if score in the game produces this bad behavior, right, in this environment? And it's because we didn't think of an environment like that. What we had in front of us were probably simpler levels, simpler environments where the choices were much more simple. The choices were, I can win with a lot of points. And if I lose, I get fewer points. So score and winning were correlated at development time when I designed the reward function, but they're no longer correlated at deployment time. That correlation breaks and that gets the robot into trouble. So if we take this idea that I'm only looking at some development environment, and that's what drives this disconnect between theta, what I want, and theta tilde, what I write down, and try to put it into math, right? It's basically something like this. The key idea is that the specified reward is not the same as the true reward. So we should not expect that the behavior it induces everywhere in any environment is the right behavior, but we do know for sure that it does induce good behavior somewhere. It induces good behavior on the environments used by the designer during development time to tune and test the reward function. So on those development environments. So whatever the designer landed on as the specified reward, the behavior that it incentivizes on those development environments for that specified reward has to be good behavior. What does good mean? It means it has high true reward. So it's good respect to theta, even though you're optimizing theta tilde. Another way of saying this more naturally is that what you specify is contextualized by the state you specify it in. So robots have to interpret it in that context, not in literally. In math, in an equation, it looks something like this. The probability of me writing down theta tilde doesn't just depend on theta star, the thing that I actually want. It also depends on the development environment I'm looking at. And our model says that if you look at what behavior theta tilde incentivizes in that development, in that set of development environments, so if these are the approximately optimal trajectories with respect to what I specified, theta tilde, then the higher the reward of the behavior with respect to theta star, what I actually want, the more likely I am as a designer to write down theta tilde as my reward. Okay, so I'm gonna only write down theta tildes that in MDevel produce high theta star reward. Visually, and I flip this to a cost. So if this is the space of trajectories and this is negative reward or cost, you can say, well, maybe this is theta star in the development environment. So according to theta star, this is what the cost is. Now, I might write down theta star, but I might write down something else. What this model says is I'm probably not going to write down this cost function, because this cost function, when I optimize it, produces a trajectory that's really bad with respect to theta tilde. I'll catch that. I'll fix it. I'll specify a different theta tilde. So I'm not going to write down this red one. But there might be a lot of other ones that agree with theta star and MDevel. And this model says, you know what, the designer might actually go for one of these because they don't have a way to disambiguate because they're just thinking about MDevel. And then if that correlation breaks at test time, at deployment time, right? If all of these green now all of a sudden produce different optima, this is where the problem is. So in the boat environment, concretely, if you imagine that you have a space of thetas that are like maximizing winning is one, maximizing score is another, minimizing winning, minimizing score, maybe many, many other thetas that are possible. The person says maximize score, so they pick theta 2. Instead of just optimizing theta 2 everywhere, using this kind of model, what you can do is you can say, what the robot can do is you can say, okay, well, let me look at MDevel. Let me look at the behavior that maximizing score leads to in MDevel. It's this behavior where I get a lot of points and I win. And now let me look through hypothesized thetas and figure out which ones agree with that. Clearly maximizing score kind of by definition does. Clearly minimizing score or trying to lose do not, but maximizing winning also agrees with that. And now the magic thing that happens here is not that the robot knows that you meant maximize winning. It can't. But very importantly, what it knows is that based on what you looked at, it can't disambiguate whether you meant winning or score. And I think that's really magical because it has sort of this uncertainty where it knows some things that you said are correct, but it doesn't say literally what you said is the entire truth. So it's like, well, okay, well, you said score, you could have meant score, you could have meant winning. And then that gives it this updated belief on what data might be, on what the true data might be. And then what it can do is it can plan an expectation, so sort of hedge its bets. It can even do risk-averse planning, right, and try to be conservative with respect to any of the data that are sufficiently probable under its posterior. So in a motion planning setting, again, with the arm and the people around, what's hard here is in part that if I want to get this arm to move properly, I have to balance a lot of different considerations. I have to balance efficiency. I have to balance distances, but there's distances to fragile objects, which I might want to put more emphasis on than distances to things like tables. There's distances to the person's head, which I want to put a lot of weight on, because getting really close to people's heads is really uncomfortable to humans, right? And so there's all these different considerations. What I would do is I look at a set of environments. Here's one example, and I tune my cost function until it produces good trajectories on those environments. And we went ahead and did that in the lab. And we picked, I don't know, like 20 or so environments. We picked a cost function that worked well. And then eventually, not immediately, but eventually we encountered a test environment in which the optimal thing to do is this. I don't know why. I don't know what's weird or different about this environment, but according to the cost function that I specified that worked well in all these other ones, here, what it turns out is the optimal thing to do is to plow through the base. Now, can I fix this with hard constraints? Yes, but I want to kind of remind you of what I was talking about in the beginning, that hard constraints are not the be all end all. You have to still specify thresholds on those and so. So the alternative approach here is to not just optimize theta tilde. Just because I specified theta tilde doesn't mean that that's definition of theta. So using this kind of model that I was going through earlier, the robot sort of thinks back to the development environments. It does this inference on what the theta might be, kind of conditioned on having seen this theta tilde now. And in this environment, it plans, in this case, we just plan an expectation using that posterior. And all of a sudden, the robot hedges its bets, and all of a sudden, the behavior is not as obnoxious anymore. And so this technique, essentially, we found leads to better behavior with sort of less time being put into designing the cost. And that's all great, but this is all so far with the boat and with the motion planner. It was all in situations where we told the robot what are all the features that might be important. And all they'd have to do is say, okay, you told me to balance them this way, but I actually think that there's, other ways to balance them. So we still had to provide it, like winning is a thing that people might care about. How does the robot know that, right? In reality, that's what might be really hard, is to know what are all the things that are important. A little toy example where we got closer to that setting was this little grid world where there's these different kinds of terrain. There's grass and a target, and there's dirt. And then there's lava, which is supposed to be really bad for you, but it's not present in the development environment. It only shows up at deployment time. And then what we do is we, instead of just getting access to the features saying, okay, this is dirt, this is lava, the robot doesn't know any of that. The robot just gets some raw sensory information about the terrain type. And the reward function is based on environments that don't have any lava. Essentially what we do is we train features for the things that we observed in the development environment. So we teach the robot to recognize grass and target and dirt, and then we define a reward function that weighs these different things, okay? But we don't say anything about lava because it's not in development set, so we sort of don't think about it. And then we do the inference based on development environments, and we test it in environments that have lava. And what we see is that risk-sensitive planning on that posterior that we derive based on deployment ones ends up avoiding lava. So this means that it implicitly knows, not that lava is bad, it doesn't know that, but it knows that it doesn't know whether lava-like things are good or bad. Without knowing what lava is, it's just it has access to the raw feature space, and implicitly in its hypothesis space of thetas, there's something that picks up on lava-like things, and then it knows that it doesn't know whether those things are good or bad. That's what's happening. So I think that's pretty promising. Of course, instead of a lava, if we had gold, and gold is a good thing, right? The robot would avoid the pot of gold because it doesn't know based on the development whether gold is good or bad, right? So it's not that it knows that lava is bad, I think. But again, I think the key here is that it knows that it doesn't know. So unfortunately, avoiding the pot of gold, what does this mean in practice? Let's go back to autonomous cars. So with autonomous cars, you look at a bunch of environments where you want your car to make progress, et cetera, et cetera. You write down your theta tilde. And then the robot has this posterior. Now, if it's risk averse with respect to this posterior, or even if it plans an expectation with respect to this posterior, it does too much hedging because it turns out there's many things, there's many interpretations that are consistent with what you said. And this is an issue now because it's not, you don't have a useful robot anymore, right? The more there's uncertainty in theta, the more you're sort of paralyzed because everything you might do could be bad. And so this can't be the end of the story, right? It can't be like the person gives us one theta tilde, we have a posterior based on that, and in perpetuity we do risk averse. And so a lot of what we've been playing with recently is this interactive way to design reward functions where we kind of help the designer out by saying, okay, you said theta tilde, thank you. I'm going to look now at my posterior, and I'm going to sort of try to hallucinate environments where I would have uncertainty about what to do, where members that are high probability thetas in my posterior are sort of now disagreeing with each other. And a way to do that is to search for environments, M, that maximize expected info gain you would get if you showed the person M and they would define or revise the reward function based on M. And so what this ends up looking like is that you're looking for environments, and you have to parameterize environments somehow. I mean, you kind of have to say, like, here are all the ways in which things can be configured in the world. But then you can look through that, and then you pose these environments to the person where your possible rewards, score and winning, so to say, are all of a sudden disagreeing, where they incentivize different behaviors. And indeed, we find that these environments that the robot proposes end up being bad, end up being environments where something bad happens. And this is like this way for the person to now look at that, recognize that, and then fix the reward function. So it's like assisted debugging, essentially, of your reward function. And so by exposing the designer to these kind of edge cases, these things that happen where that they didn't think about, where they end up getting poor behavior with what they specified, and then revising based on that, you end up sort of lowering, kind of converging to a better reward function iteratively with the designer much quicker. And so in orange here is the kind of active method. And in gray, it's sort of if you just let, the world sample environments without trying to actively expose the person. So this is work in progress, but I think it's pretty, I'm excited about this notion of, we call it assistive reward design. It's like I'm actually building AI tools that can help me specify these costs or reward functions for a particular task by taking my attempts and then exposing me to edge cases that I might have not thought about. Going even further down this, when you want to represent your reward as a neural network, because you really want to be able to learn the features in a more complex, we can do some things without neural nets in like the lava environment and so on, but the real world is much more complicated. And so if I want to represent reward functions and neural networks, I have a lot of problems now because I have to have a posterior over neural networks, right? So we took a first step towards this, but I don't have an answer. I have no idea how to do this right. But something that we tried doing was to, instead of actually, having a full posterior, which we usually do with MCMC sampling, what we did is we took some inspiration from some recent work on ensembles, and we said, okay, we're going to maintain not one reward estimate. We're still going to have a few. It's just going to be an ensemble of a few. You can think of them as a few samples, basically, from the posterior-ish if you squint, right? And then in order to generate new environments, maximizing info gain, what we can do is look at this ensemble and say, well, where does it disagree on what the reward is? And we're going to say maximize ensemble disagreement when you're generating environments and behaviors, but subject to the constraints of the real world. It has to be realistic somehow. By the way, this is pretty hard. You have to train something that says whether it's realistic or not. So these are the kind of a learned dynamics model that you have about the world. Practically, we try this out in a car racing environment. It's still pretty simple. It's not nowhere near the complexity of sort of more fancy simulated autonomous driving they're able to do before. But, it is an environment where the robot doesn't know dynamics and where the reward function is represented as a neural network. So what we did here is we pre-trained dynamics model that consists of a VAE for encoding and decoding frames, an RNN for modeling transitions, and this partially observable environment, and a mixture density network that models the stochastic transitions. And here's an example environment, and here's the trajectory that it creates. So basically, when you do that optimization for ensemble disagreement, you create this environment where essentially what the car does is it goes towards the edge of the road and drives on the edge, because it has uncertainty given what it knows so far about the reward function, whether being on the edge of the road is okay or not. Like it knows that being off the road is bad. It knows that being in the center of the road is good, but it doesn't know whether the edge of the road is bad or not. So that's kind of the edge case, the sort of the thing that helps it gather information about what it is that you want. And here's what happens if you don't care about getting the dynamics to be realistic. You just like produce some garbage that is technically informative if a real human could ever look at this and respond about what's going on. But, it's so the dynamics of this environment are so wacko that it's hard for us to imagine whether this would be the right behavior or not the right behavior in this kind of environment. So it's important to actually kind of ground it in that constraint of realistic dynamics. Okay. But I think overall, right, like we do linear weights on known features. We do some, shallow models on more raw sensor reinformation in simple toy environments. We do neural network representations. There's a spectrum here. And what I really struggle with is that as I go farther along the spectrum towards deep neural networks, we end up with computation problems where you have to represent a posterior over neural networks. And we end up with something much more fundamental, which is that there's so many hypotheses in your hypothesis space that are consistent with the data you've seen so far, that you have to really go back to the person so many times to actually disambiguate what's going on, even if you put computation aside and you're actually able to generate that posterior. And so I think the question that's really open for me is, where should we be on this spectrum? Is there some structure that I can assume, some inductive bias I can assume on reward functions, that on the one hand means that I can, not ask the person about hypothetical things that are not even semantically meaningful, But at the same time, I can, come up with like, oh, the edge of the road might be a problem, or the lava might be a thing, right? So that I have to be able to represent those things that the person might have left out from their initial specification. So you need that to be expressive enough for that. And I have no solution for this, but I'm just kind of posing it as a thing that bothers me these days. Okay, we're 40 minutes in. I would like now to pop back up from specified rewards to other sources of feedback, but I think this is a good time to also pause and see if there's any questions so far about what we're doing to learn to infer rewards from specified rewards, because I know it's a weird concept. The person specified something, I'm gonna just treat it as evidence. What is going on there? And if not, we can move on. Okay, so specified rewards, evidence about the reward. And we've talked about a model, an observation model for that. What about all these other types of human feedback, right? What's a model for them? And it turns out there's two types of feedback that we know, besides rewards, that we know very well how to handle. And we've been doing this as a community for a long time. So when the feedback is, here's one trajectory, here's another one, and trajectory A is better than trajectory B, we know how to take that as evidence about the reward. Basically, we say, you, the human, had two choices. I'm going to assume you're choosing based on cumulative reward of these trajectories with respect to your reward. And I'm going to assume maybe you're a bit noisy. So I'm going to say the probability of you choosing A over B given theta is proportional to the exponent of the cumulative reward of A. And I want you to pay attention to the normalizer here, right? So I have to normalize this over my choices. It was A and B, so I normalize it over A and B. So we know how to do this well. We also know how to do demonstrations well. So that's inverse reinforcement learning. In this case, it'd be called specifically Bayesian inverse reinforcement learning. The choices, when you give me a demonstration, when you tell me this is how to drive, you also have choices. The choices are now implicit. They're all the trajectories that you could possibly demonstrate. You only demonstrated one, you demonstrated roughly the best one, right? So your choices are trajectories, not just A and B, but all of them. And you're implicitly making a choice among them when you're demonstrating based on the reward. You're looking at the cumulative reward of everything, and you're picking the one that has roughly the highest cumulative reward. And again, people are noisy, so we can account for some noise here. And here we'll usually say the probability is still proportional to the exponent of the reward, but now my normalizer is more interesting because I have to integrate or sum over all your choices, not just A and B, but all the trajectories. Now this is pretty consistent with each other, right? So we have two forms of feedback. We roughly interpret them in the same way as choices, implicit or explicit, with respect to the reward. We also talked for half an hour about what to do when the person specifies a theta tilde. And I'm just going to remind you that big formula looks something like this. If you squint at it, it's that you'll specify a theta tilde that's proportional to the exponent of the reward. Now, what's going on here is you can think of it as a choice too. The choices now are not trajectories, they're reward functions that I could specify. And I specify one of them. I specify theta tilde. And I'd like to say that I specified based on the reward, but there's a bit of a syntax mismatch here, right? Like, what is the reward of a reward function instead of a trajectory? And so the way we did this in this inverse reward design framework is we said a theta tilde maps really to the trajectories that theta tilde induces in the development set. And those are the ones that should have high reward. And so basically what this model that we've been talking about was saying is just, you're going to look implicitly at theta tilde, you're going to look at other thetas, you're going to look at the reward of the optimal trajectories they induce with respect to your reward, and you're going to pick the best, approximately, again, with this sort of Boltzmann distribution. And so three feedback types now are kind of the same. So what's going on here? Well, if you think about the question that we posed, there's all these feedback types. How do we interpret them into an updated belief? Maybe we can look at all of them and think of them as these choices implicitly that the person is making with respect to the reward using the same kind of framework. And so if the person pushes on the robot, they're making a choice. Their set of choices are the external torques. They're not trajectories, they're not rewards, they're external torques that they can apply to the robot. And these external torques induce trajectories for the robot, if you think of the torque as deforming the robot's trajectory. And we can think of the person as applying the torque, right? At least as sort of the deformed trajectory has higher reward, and they're just choosing among the torques. And if you do this, then I apply my torque, and the robot's like, oh, okay, that means that that torque was better than other torques with respect to this reward function that you want. What does that mean about the reward function? Oh, it means that you want to stay closer to the ground. Great. Okay, so if I stop the robot because it's about to enter a puddle of water, I'd argue the same thing. I'm making a choice implicitly because I could have done nothing, but I chose to turn the robot off. And that choice can be thought of as a approximately rational choice with respect to the reward. Now, what's the reward of, pressing the stop button? Well, that maps to a trajectory. It maps to the trajectory that remains stopped for the rest of the time horizon. What does it mean when I do nothing? How do I evaluate the reward of that? Well, that maps to a trajectory too. It's whatever trajectory the robot was going to execute. And so by making this choice, I'm telling the robot that it's better, according to the reward function, to stay stopped than to continue along. That's information. Okay, last thing is the house of cards. So what's up with the house of cards, right? We talked in the beginning how I entered the house of cards, the room, and I know that I shouldn't clean up the house of cards. So far, we talked about sources of information that look at behavior of some form, turning the robot off, pushing on the robot, demonstrating stuff, moving, etc. So if I have a room that has a fragile vase, our metaphor for the metaphor that is house of cards, I have to see the person avoid the vase in order to figure out that the vase is important, that I shouldn't knock over the vase, according to what we've talked about so far. And we've talked about ways to do that, right? Including inverse reinforcement learning. Imagine I don't get to see this. I just entered the room and there's a vase in the middle of the room. Somehow the vase is still there and it's not the beginning of the universe. And people have been walking around this room. Now, I haven't seen them walk. I haven't seen them explicitly avoid the vase, right? But I know that they've been walking around. That should tell me that I shouldn't knock over the vase. So when the agent is deployed in an environment that the human has been acting in, and the agent knows this, the state of the environment already has information about the person's intended reward because the person has been acting according to their preferences, roughly, approximately, somewhat suboptimally in that environment. And lo and behold, we think of this as a reward rational implicit choice that the person makes. I kid you not. What you can do is you can say, person has choices. They're not about behaviors anymore because I don't observe the behaviors, but they're about states that they end up in. So they choose the state as 0 that the environment is in. How does the person choose a state based on the reward? By grounding a state into all of the trajectories that end at that state. And so essentially when the robot observes an end state, what it really observes is that the trajectories that end in that state are probably better than the trajectories that end in other states. Approximately, again, with the noise, with the Boltzmann noise. So you can think of the state of the environment itself as a choice that the person made. And so what does that mean? It means that the robot kind of thinks back and simulates the past and says, if the person wanted to break the vase, they would have gone through, that would have resulted in a different state than what I see now. It will result in a broken vase. The vase is not broken, so they probably don't want to break the vase. If they didn't care about the vase, they would have gone through, again, inconsistent. If they wanted to not break the vase, they would have gone around, and that's consistent with the state that I see now. So that's roughly what's going on. Real quick, in the last 2 minutes, in this room with a vase, the robot is told to go to the purple door, and it goes to the purple door, avoiding the vase. That's just avoiding negative side effects. What I really like is it's this really cute example. It's all toy, I know. But it's this really cute example of being told to go to the purple door, but there's this train running. And the train runs out of batteries, but the robot looks at the train and is still running, which means that it can figure out that it's probably a good idea to keep this train running. So instead of just going to the purple door, it goes and picks up the battery. It has to know about how the train works, of course. So this assumes known dynamics. And then fixes the train and then goes to the purple door. And the train keeps running. So anyway, I think that's really cute because you can sort of not just avoid, unintended bad consequences, but also figure out like what are things that people might care about, might want. Good. So I don't think AI or optimal control is about, specifying a reward and that's the robot's job is to optimize that. I think it should be about intended reward. And I fully acknowledge that intended reward is really hard because it's in the person's head. But I think we've made a little bit of progress on saying there's all this information that is out there, including the person specifying a reward. It's really useful information about what people want. Let's look into it. Let's stop over learning from the specified rewards. Let's actually learn sort of the right amount of information from each of these sources. And a way to do that so far that's been okay. I think it could be better, but it's been okay. It has been to think of all these sources of information as choices that the person has implicitly made that link that back to the reward function. A lot of what I worry about these days is that we can't slap a Boltzmann distribution. You can't slap a Boltzmann distribution on it and say, that compensates for human suboptimality. Like it doesn't. People have systematic biases. And so it's a lot of what we worry about now. And I'm happy to talk more about that because all of this framework is like people are optimal or approximately optimal, and they're not. So I think we can do much better if we account for that. And so overall, I think I've talked a lot about rewards here, or the optimal control framework. But I think that regardless of what your method of choice is in terms of how you do this task specification and what algorithms you use, I think I just suggest that it's a good idea to start thinking about our difficulty in getting that specification right and thinking about how to obtain specifications that are going to be robust to new environments that the system is going to be exposed to. Good. So I'm going to skip, I'm out of time. So I'm going to skip a bunch of things and say thank you for listening, and thanks to my collaborators and students who've been, actually doing this work that I get to brag about. Thanks everybody for listening.
Yeah, thanks. Yeah, thanks, Anca, for this very interesting talk. Now let's open up to questions. So if you have any question, feel free to post in the chat box or directly unmute yourself to interact with our speaker.
Hey, Anca, thanks for the great talk. I have a question regarding the transfer learning or meta learning setting. Like, how does the learn reward generalize to a new driver or like new vehicle? Have you considered some situations like this?
Yeah, so I think we've mainly looked at environment changes, but of course, environment changes could mean different dynamics in theory. We haven't looked at different dynamics. The way that would, if your reward function needs to work on all of your fleet, for instance, right, and on new vehicles that you might be introducing, then what you would want to do is incorporate that sort of degree of freedom as you're searching over new environments to expose the designer to. So there was this bit in the middle of the talk where I was talking about what we might call assisted reward design, where you say, here's my best guess, and then the robot tries to figure out based on its posterior where it still has uncertainty, and then shows you an environment where it wouldn't know what to do. I think that generator, right, of environments has to be as rich, right, has to be able to change as many things as you'd like your reward function to transfer to. Yeah, and we haven't played with dynamics. We've played mainly with initial configurations of things and stuff like that.
Thanks.
Mm-hmm. Yeah, and I have a kind of question. Since during the talk, we have been introduced different like frameworks to deal with the different types of intended reward. For example, in the boat competition case, it's like, yeah, there can be this different scenario, either maximizing the score where like winning, where like in the later on the human case, when they push the robot, is like kind of giving interactive feedbacks. Or in the base case is like environment feedbacks. So it seems all these different scenarios for the intended reward. So right now, like, should we do we have, are you trying to combining all these different, is there a framework we try to unifying all these different scenarios, or is still like we kind of need to predetermine for this task or for this scenario, is this case, and then we go for that?
Yeah, I'm so glad you asked that. So with this, reward rational implicit choice, I think of it as that unifying framework. And let me explain how it relates to your question of, how do I use that based on the, so what it does is it says, whatever feedback comes at you, think about it as a choice that the person makes, right, with respect to the reward function. You still have to figure out what we call a ground. You still have to figure out how the choice maps to trajectories or distribution over trajectories, so that you can say the person has looked at these choices implicitly and picked the one that has the highest reward, right? So that's the part that whenever you want to be able to introduce a new type of feedback, you have to specify, okay, well, this is how these choices that the person has ground into trajectories, right? For instance, when we introduced the like turn the robot off type of feedback, right? We had to say, okay, well, the way that's a choice with respect to the reward, because the reward of like the person turning you off or the person doing nothing, those are not actions in the MDP that you're dealing with, right? So you can't evaluate the reward directly of that. So you have to ground it into trajectories or distributions over trajectories in the MDP that you're on, which is what I was doing when I was saying, well, if the person turned you off, that grounds to like staying stopped for the rest of the time horizon, which is a trajectory. If the person didn't turn you off, that grounds to letting the robot continue. And so that is something still that is not done automatically, that every kind of behavior type, we have to think about, well, how does this ground, every choice, how does this ground into sort of trajectories in the robot's MDP? But once you have that, right, you're always consistently interpreting every feedback as a choice the person's making that's approximately rational. And so that means that you don't have to say, well, for this task, I'm going to use this feedback. For this task, I'm going to use that feedback. You can just let people, leak their information. You enter the environment, the designer told you something. That's, the specified reward that has updated your posterior. You enter the environment, you see, a configuration, right? A state of the world. That's information that should then, do another update, right? Your previous posterior becomes your prior. Now you got more information. Now you have a new posterior. The person you start doing stuff, the person pushes you away from them because they're not comfortable with how close you are, right? Bam, that's more information. And so you can do this kind of this continual learning, right, of what the reward is by combining all these sources of feedback that are getting thrown your way. The other thing that I'm excited about these days related to that is to do active learning or active querying that reasons about which specific type of human feedback would be most informative. So if I don't want to just let the person passively, say, oh, I'm going to push you away here, or I'm going to demonstrate something here, can you actually kind of take this, matter into your own hands and be like, I think that, what I should do here is execute this trajectory and see if the person corrects me, because, that correction is going to be more informative than showing the person two trajectories and asking them to choose or something like that. So it doesn't have to be passive, but I think in a sense, the passive vision is kind of nice. You just, you keep resolving more and more of your uncertainty as you experience more feedback. So we call this framework reward rational implicit choice. There's a little write-up on it that you can look up. Again, it's not fully automatic because you still have to specify the grounding for each new feedback type you want, but it does give you the ability to think about all of these different types in a unified way.
Got it. Yeah, that's very helpful. Yeah, thanks. And yeah, any other questions?
We get a question from Pars from the YouTube. Could you please elaborate on how you see under-actuation properties here and maybe give a simple example?
Yeah, so that was in the intro, right? This is some work that we did with Dorsa Sadig when she was still a student at Berkeley, and this was before this work. The way we were thinking about autonomous driving was, at least largely in academia, was to say, I'm going to make predictions about the human, and then I'm going to plan a trajectory for my robot that avoids collisions with the human and still achieves the robot's goals, right? So this was like robots that stay out of the way. There were some proposals to treat things in navigation, not in driving, but pretty similar. Folks like Pete Troutman and Wolfram Burgard had proposed some models that get at this problem by proposing that we kind of we should plan collaboratively. So we should do coupled planning, right? We should think of the human and the robot as being in a team. And that sort of captures this mutual influence that they have, where it's not just the human goes and then the robot is stuck with whatever the human plans and has to respond, but it's sort of jointly, the problem is that autonomous driving is a general sum game. You're not in a team. You are actually competing sometimes, right? For efficiency. And so the work with Dorsa and then later with Jaime that we were doing was to account for this general sum nature of the problem. First, the underactuated dynamics part was to say, let's think of it as an underactuated system where we control the robot's degrees of freedom, but actions that the robot takes, controls that the robot applies, steering and acceleration, dash braking, those controls, those actions don't just change the state of the robot, they also change the state of the human, because they have an influence on the action that the human decides to take, which in turn changes the state of the human. So before, the state of the human was evolving independently of the actions that the robot was taking. And now the idea was to be in this system where, and it's like an inverted pendulum, basically, right? It's like, it's the same kind of thing. It's just that dynamics model is much more sophisticated because it's a cognitive computational model of how the person makes decisions based on observing the robot's actions. And then with Jaime, we took it all the way to a general sum game and solved it hierarchically that way. It turns out you can do that with dynamic programming in some discretized space, and then you can use that for your continuous control by using kind of the value functions from the discretized space to guide your low-level control. And so that was another piece of work. But yeah, really cool to think about this mutual influence between humans and robots.
Okay, yes. So due to the time limit, let's take the final question. It's a quite interesting one posted in the chat box by Mert. He asked also if there is any chance that the leaked information can be harmful in some cases because of bounded rationality
of humans. Yes, Mert, that is absolutely right. So at the very end of my talk, I was saying, well, isn't it great that we have this framework? Everything that people do is information if we think of it as approximately rational. And the reality is people are bounded rational or suboptimal, and we've been finding in a paper that I just can't get published for some reason that I love, but every time we submitted it like 2-3 times now and it keeps getting rejected. But I love this paper, so I'll talk about it anyway. So we've been finding recently that if you assume rationality or approximate rationality, but the underlying, the human producing this data has a systematic bias, like myopia, like not knowing something about the world, like, there's prospect theory, there's a bunch of different things that you can assume that the person has. So if you're modeling the person with Boltzmann rationality, kind of trying to paper over those systematic biases with just noise, it turns out that you can make very poor inferences to the point what we're suggesting is right, you're better off sticking to your prior instead of trying to read anything into it. It's going to completely lead you astray. And so that's pretty stark. And to a certain extent, it was unexpected. I assumed that, of course, it's better to know the human model instead of, assuming Boltzmann, you get better inference that. Yeah, sure. But like what was so surprising is just how poorly this can go. You can get really, really bad inference from this. And so a lot of, what we're thinking about these days is what are ways to account for that human suboptimality without, kind of giving up and going home. Because if I want to infer rewards, I'm a little bit stuck. There's no way without having a way to link this internal thing that I never get to observe to some sort of human action, human feedback. And so, yeah, we're thinking about what to do there.
Okay, cool. So let's thank our speaker again. And yeah, so today is actually the Chinese New Year, actually. So wish everyone a happy, like tomorrow. So today's the eve. So yes, and stay tuned. We'll look forward to see you next time. Bye.
Take care, everyone. Thank you so much for having me.